So now let's consider the concentration profile change for diffusion. Okay, what are we looking at? We are looking at a binary phase diagram, right? Binary phase diagram. Left side is, I think this side is pure nickel, sorry, copper. The other side is pure nickel. How do I know? Well, the top is copper percentage, bottom is nickel percentage, 100% is nickel on right side, 100% copper on the left side. Okay, of course, copper has a lower melting temperature than nickel. Okay, and above liquidus line, I have liquid uniform liquid phase. Below solidus line, I have uniform solid solution. And then at very low temperature, I have another curve. We call it quite often miscibility gap, right? Okay. But anyway, the 2 points that we chose are within so-called single phase region, right? The 2 points that we choose are within the single phase region at what temperature? 600 degrees C. Okay, single phase solid solution. Let's say we take these two compositions. Okay, one piece at 20%, the other piece at 40% of nickel. I'm just considering one of them, right? Okay, what types of diffusion? Interstitial or substitution by vacancy mechanism? Interstitial diffusion or substitutional diffusion by vacancy mechanism? Substitutional, right, by vacancy, because these two elements are very similar, like copper and nickel, similar metal, similar valence, similar atom size, right? So of course they can only go through diffusion by so-called substitutional diffusion, but not by exchange, but by the vacancy mechanism, which is quite often very slow. Let's put a piece and another piece, 20 and 40 together, put them jointly together. What I want you to consider is how would you plot the change of the concentration profile for, well, like 3 conditions. One is T1 equals 0. What does that mean? You just put that two pieces together. How would you draw the so-called concentration profile? C, right? Concentration profile is change of concentration with respect to distance or location. How would you draw that one? 20, 40, right? So this is what I'm going to draw. Initially, T1 equals 0, like this, right? To the interface, to the left one, let's say I have 20% of nickel. To the right side, I have 40% of nickel. At the boundary, I have a very sharp change when the time is 0, right when I put it together. Make sense? And what about at the t is a finite time? Not too long. How would you draw it? We said, okay, substitutional diffusion quite often is very slow. So as you can imagine, very far away from your original interface, very far away from the on the other side from the interface, the concentration should not really change, right? So I would, far away, I would keep the same concentration. But in between, remember, I'm in what phase region? Single phase region. Based on what you learned, the phase rule, that's 1 degree of freedom, which means what? The concentration, that intensive parameter, that concentration within that single phase can change independently and also continuously. Make sense? So if I'm going to draw, do you see something like this? For finite time of t2, I'm going to have something like this. Of course, how deep this transition would be depending on how long, right? At the very beginning, it should be more like this, right? Well, towards the end, it will be more and more gradual. But it's a continuous change. Why? Because we are in the single phase region. I have 1 degree of freedom. Means that intensive parameter, which is composition, can change continuously with location. Independent. Make sense? And then the last one. When t goes towards infinity, very, very long time later, what is going to happen? Well, I'm in single phase region, right? Let's, for simplicity, assume this piece and that piece initially are similar size. So what would happen? I'm in single phase region, so in the end, I'm single phase, right? Single phase and uniform. This is going to happen, right? Completely uniform after infinitely long time. Make sense? When you consider this, okay, start with 2 distinct compositions. Single phase, initially a so-called step function, a sharp change in composition, become gradual change in composition, becomes completely uniform. And this gradual change is a result of we are within single phase region. And the diffusion is typically downhill, which means the solute, if we are considering going from high concentration to low concentration. But in reality, as what you learned before, for the Kirkendall, one is going, the other one is also going the other way. Make sense? Not only nickel is diffusion, the copper is also diffusing in the other way. Make sense? Okay. So now